In this video, I will introduce the idea of limit. This is not going to be the rigorous definition yet. It will be mostly some examples, hand-wavy, heuristical, just to gain some intuition about what this concept of limit means. And once we are comfortable with that, in a later video, I will introduce the formal rigorous definition. As a first example, let's look at this function. I'm calling it f, and it's defined by this equation, f of x equals x squared minus 1 over x minus 1. This function is defined for all values of x, the domain is all the reals except 1. F of 1 is undefined. There is a little simplification I can do. I can factor the numerator as x minus 1 times x plus 1, and then I can cancel x minus 1 at the top and bottom, giving x plus 1. Except this cancellation is only okay when x is not 1, because when x is 1, the original function was undefined and the new function is defined. So to be very precise, I'm going to give a name to the original function and the new function. I'm going to call f the original function and g the new function. Then we're saying at 1 they're different. F of 1 is undefined, but g of 1 is 2. Everywhere else, the two functions are the same. I can use this to sketch the graph of both of them. Let's start with g because it is easier. G has graph this line, it's just a line, and at 1 is equal to 2. F, on the other hand, is exactly the same except at 1 is undefined. So the graph is going to look exactly the same but with a hole at 1, which I'm going to exaggerate in the picture. So it's just a line but missing a point at 2. So looking at this graph, f of 1 is undefined, but it's undefined in kind of a silly way. It's just because there is 1 point missing. But if I look at other values of x, in particular close to 1, they are all suggesting that they want f of 1 to be 2. If we had to choose a value for f of 1, it could be 2. To a certain extent, morally, f of 1 should be 2, even though we forgot to define it. So when this happens, I'm going to say that the limit as x approaches 1 of f of x is 2. And I'm going to represent it with symbols like this. Lim x arrow 1 f of x equals 2. And that means that even though f of 1 may be undefined, as is the case here, it kind of should be 2 because this is not a definition, this is just an idea, and for now it will work. If x is very close to 1, but not 1, then f of x is very close to 2, suggesting that when x equals 1, f of 1 should be 2, even though in this case it isn't. For a second example, I'm going to look at the function defined by this equation, f of x equals 1 minus root 1 plus x over x. For this function to be defined, the inside of the root must be non-negative, so the domain of this function is all values greater or equal than minus 1 except 0, because I'm dividing by x. So f of 0 is undefined. And I wonder whether f of 0 is undefined by, like in the previous example, that if I look at the graph, it's a nice graph near 0 except with a hole with a point missing. I'm going to look at this differently. I'm going to try to plug in a few values and see if that is what is happening. So I just use a calculator, this is what f of 1 is, and now I'm going to take values of x closer to 0, and see what the values of f are. So this is what f of 0.1 is, and 0.01, and I'll take points closer and closer to 0. And I think I see a pattern here. When x is getting very close to 0, f of x is getting very close to minus a half. So this suggests that, like before, the graph of this function near 0 looks nice, except there is a hole missing at 0. If I had to choose a value, I could choose minus a half for f of 0, except it is undefined. So like before, I'm going to say that if x is very close to 0, but not 0, then f of x is very close to minus half. And again, the graph will look nice, but just with a hole. I could try to do this algebraically, like before, instead of with a table of values. In this case, a sort of simplification I can do is to multiply and divide by the conjugate of the numerator. I invite you to pause the video, multiply it out, try to simplify it as much as possible, and then continue watching. I'll go quickly through this. If we continue manipulating this algebraically, we can get rid of the square root at the top and get to an expression where I can simplify by removing an x from the top and the bottom. But that simplification can only be done when x is not 0. Okay, if that went too quickly, pause the video and try to reconstruct these steps at your own pace. But the same thing as before is happening. This function is equal to another one that is well defined at 0, except when x equals 0. So the new function, I'm calling g again, is this function. It's perfectly nice and smooth near 0, and the value at 0 is minus a half. And the original function has the same graph, except with a hole at 0. So I'm going to say, like before, that the limit as x approaches 0 of f of x is minus a half. And what that means is that even though f of 0 is undefined, if x is very close to 0, but not 0, then f of x is very close to minus a half, suggesting that the value at 0 should be minus a half. To conclude, in summary, the limit as x approaches a of f of x equals L means that if x is very close to a, but not a, then f of x is very close to L. This is just an idea. The formal definition will come later. But first, in the next video, I'm going to introduce some examples of functions that do not have a limit and explain why.